Hello everyone, today we are going to discuss the problem that is routing oranges. In this question, what we will do, we will first discuss the question and then we will see how to approach it. So here what it is saying that you are given an n cross m grid, and in this grid there are three kind of values that you can expect. In a grid you can expect three sort of values. One is either it could be 0. When we say it can be 0, that means it can be an empty cell. If we say it is 1, that means it's a fresh orange, and if we say it is 2, that means it is a rotten orange. So our goal is, what it is saying, that whatsoever oranges who are in 4 directionally adjacent to the rotten orange will get rotten as well at the end of the day. So we can see that this rotten orange was in adjacent with this and this orange, and that's why these two will get rotten as well. And once these two are rotten, the adjacent of these two will get rotten as well, that is this and so on. So at the end our goal is to find out, first thing is, are we able to mark all of them, are we able to reach till all the fresh oranges and mark them as rotten? If not, then return -1. That is, if at the end of the day there is one orange that is not reachable, then mark -1 or return -1. Else, if it is possible to rote everyone, then tell me the time or the minimum time it will take for all the oranges to get roten. Fine. So it seems like a graph problem where you are given a node and you have to reach till all the other nodes, right? First thing is that it looks like a graph problem. Fine. Now, one thing to keep in mind is, whenever you are asked that what is the minimum time it will take, make sure that you are using a BFS approach. Now let me tell you, in this question, when I was reading this question, why I thought of a BFS approach and not a DFS one. So when you are given a rotten orange or rotten node, what happens in DFS, you go till the very depth. So you will go till the very depth of it, and you might miss on some nodes which were in adjacent to this particular node. And when you come back to these nodes, the time would have increased drastically. So to avoid this, we will use BFS. And the reason why we are using BFS, because we are going level wise. And when we need to go level wise, we go with BFS, right? Each level will tell us that how many oranges will get roten at this stage. So once this was roten at the very start of the day, and in the next level these two will get impacted, in the next level these two will get impacted, in the next level this will get impacted, and in the next level this will get impacted. So that's the reason we used BFS. Okay, now let me show you a diagram to explain you one more thing. So let's suppose there was just give me a minute. Let's suppose there was a grid given to us, and these are all the nodes that you can expect out of it. And let's suppose this is roten, okay, and this is roten as well, and there are some fresh oranges here, 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 and here. Okay, so it is asking that give me the minimum time it will take for all the fresh oranges to become roten. Okay, so we know that this and this will be the first nodes that will get roten. Why we are saying that these two are going to be the first nodes that will get affected? Why? Because they both are adjacent to some of the roten oranges. So it doesn't matter that you just have to pick one roten orange. No, you can pick all the roten oranges together and tell me what all adjacent nodes or what all adjacent fresh oranges are there which are surrounding these roten oranges, and add those fresh oranges, mark them as roten, and add them to the queue, and then explore the next level. So this is how we are going to go. So we know that when applying a BFS solution, we always use a queue, right? So that's what I'm doing. I'm adding all the roten oranges that are there in the very start. See, in this for loop, what I'm doing, I'm exploring all the paths which have grid of I and j is equal to 2. When we say equal to 2, that means roting oranges. rotten oranges. So we will pick all the oranges that are rotten and add it to my queue. No matter if it can be like 3 oranges are affected or 4 oranges are rotten or 5 oranges are rotten, we do not care. We will pick everything up and add it to our queue. Once we are done, what we are going to say, okay, now we have all the oranges that are there with me. Okay, once I have all the oranges, all the rotten oranges, what I'll do, I'll say okay, these are the three, let's suppose there were 3 rotten oranges, that is this and this, and I added all 3 of them together. Now I'm seeing how many values I can pop on the first level. So for that, what I'm doing, I'm calculating the current size of my queue. That means all 3 of them, if I pop, that means I am at level 0 right now. So until and unless my size become equals to 0, I'll go ahead, I'll continue, and every time what I'll do, I'll pop up from my queue. I'll say okay, tell me all the 4 direction through to which my rotten oranges can reach. And I have a condition that we should not go out of bound. Okay, we should not go out of bound, and my value should be equal to 1. If it is not equal to 1, then we will continue. Now in here we are sure that we are not out of bound. We are at a place which is 1, which means which have a fresh rotten orange. So I'll add that particular block on top of my other elements on queue, and I'll mark it as 2. Why I'm marking it as 2? It is a sign so that I do not revisit this node again. I am making this 2 saying that this is rotten. Do not add this particular node in your queue ever again if it comes in the future, because that's what we are saying, that only pick up the nodes which have 1 as their value. So now we are making them 2 so that we do not revisit them. Fine. We will go on doing this again and again and again until we have popped out all the 3 starting levels, all the rotten oranges that were there at the level 0. Once we have pulled out everyone, we would have added some other adjacent other fresh oranges which were adjacent to those particular rotten oranges. What I mean by this, let me change the color. See, in here this and this were rotten oranges, right? So we would have saved the indexes of these rotten oranges. In this case it would be 3, 0. Okay, in this case it would be 0, 2. In this case it would be 2, 3. So I have added all these values inside my queue. Okay, and then I'm saying that okay, for each I'll keep on popping all 3 of them, and meanwhile I'm popping it, I'll make sure that I add all the adjacent nodes as well. Correct? So for this I have added this, and for this I have added this. So currently at this level I will have 2 values to encounter, and once I'm done with all 2 values, I'll pop them and I'll add all the adjacent values that are there for these 2 values. So it's like there are blocks that I'm picking. Every time I'm picking up levels, that at level 0 these 3 values are rotten. At level 2 these 2 level 1 these 2 new values got added. In level 2 these other 3, 4 oranges get added. So that's what I'm doing. Every time when I'm done with each level, I'm incrementing my time. So I'm only incrementing my time when I'm done with some particular level of rotten oranges. Then only I'm adding time to it. And at the end of the day, I'm just checking that if at any point when I'm done traversing through all my rotten oranges, but still if I have any of the block left which is actually 1, which is actually a fresh orange, that means that is not reachable, and I'll return -1. Else I'll just return my time. That's all this question is about. It's a very good BFS approach, BFS question. Just go through it, try it yourself. It will give you a lot of confidence. And I'll provide this code in the comment section. Let me know if you need any other help. Thank you. Before we go on, let me quickly discuss the time complexity and space complexity as well. So when we talk about the space complexity first, so the only space that we are using is this queue, correct? This directional array that I'm using to keep track of all the 4 direction is constant, so we are going to ignore it. But the major time that we can major elements that we can use is this queue, correct? And we can assume that all of the values will get added in this queue some way or the other, right? If all of the values are rotten, let's suppose at the very start itself all the values inside my grid is already written, in that case I'll add all of them inside my queue. That means my queue can hold at max, in the worst case all the elements can be added to my queue, and that will lead to a space complexity that is O of n cross m, where n cross m represent the total number of rows and total number of columns inside my grid. So if we talk about the space complexity, it is O of n cross m. Fine. If I talk about the time complexity, right? So see, this will take n cross m, fine. This will also take n cross m, correct? And if I change the color, and let me clear it up so that, yep, let me change the color to something. Okay, I think this is good. See, this will take n cross m time, okay? This will take n cross m time, right? Now the only thing left is this one. See, this is a BFS approach we are using, where we are picking each node at the end of the day, right? We are picking up each node at the end of the day in the worst case, correct? And then we are exploring all the four direction of going through this particular node, right? So in the worst case, it can go something like n cross m plus, what we are doing, we are exploring all four direction for this particular node, correct? So we are going in all four direction for each node, so it will be 4 of n cross m. So at the end of the day, time complexity comes out to be n cross m plus 4 of n cross m plus n cross m, right? Which ends up, if we take the if we take the average of this, or we talk about the average time complexity, then it would be n cross m. So this will be our time complexity, and our space complexity we have already discussed, that will be n cross m as well. So it's a pretty good solution, I would say. That's all for this video. Thank you so much. Bye.